introduction. Thank you, Derek. Derek mentioned the fact that this was last minute. I was sitting in a class last Wednesday, and I got a note from Cassandra Arnold. And for those of y'all who know Cassandra, you know she works in the department that assigns corrective and preventative actions. And I get a note from from Cassandra Arnold says, "Do you have a minute to talk?" And I'm thinking, oh no, I do not want a capital. I do not want a capital. And so
the principal's office.
Yeah, unfortunately, my thing said available. So I had to write back and said, yeah, what you got, Cassandra? And she says, "Can you give a presentation?" I'm thinking, yeah, I can give a presentation, just don't give me a kappa. So presentations are easy, kappas are hard. Quick question before we start. I want y'all to think about your experience in actually going out and measuring or testing something. Okay? Think about that and think about what it is that you try to do, what decisions you try to make before you decide which piece of equipment you're going to use to perform that measurement or test. Okay? What would that be? What decisions do you make?
Right, accuracy.
Accuracy? Precision? Range. Good. Environment is, thank you. Great. Okay? But basically you look at it and you say, okay, this has got a tolerance of, I don't know, plus or minus 50 microns. Can I measure that with a steel scale? Obviously not. Can I measure that with a pair of 6-inch calipers? Probably not. We need something with a little bit more precision than that. Okay? This has a tolerance of plus or minus an inch. I can measure that with a ruler. Right? You make those kinds of decisions. Okay? Where I came from before I went work for Medtronic, I worked for a company that made, as a matter of fact, I worked for Johnson & Johnson, and we made disposable contact lenses. Okay? Who here wears contact lenses?
Oh, I do.
As it turns out, I got in contact lenses. These glasses don't provide any correction. But that's the God's honest truth. I only wear them to keep the wind out of my eyes.
It's all for show.
Yeah, no, face furniture. No, it's just to keep the wind out of my eyes. But disposable contact lenses, right when I went to work for J&J, they came in 3 different materials. And so we started measuring, and we would do a test method validation for each of those 3 different materials. Even though a contact lens is a remarkably simple, if you think of this lens, it's a remarkably simple piece of curved material that all it does is bend the light, either this way or that way, right? That's all it does. And when you measure, when you look at optics, the only standard for the power of a lens is the index of refraction, which is basically how much that material bends the light, and the radius of curvature. Both things which are relatively easy to measure. So why would we need to validate that piece of measuring equipment for material 1, and then redo it for material 2, and then redo it for material 3? When quite frankly, the only difference between materials 1, 2, and 3 was the amount of silicon that was in the lenses so that they would be more lubricious on your eyes and wouldn't dry them out. Why do we need to do that? Do we need to do that for all different sets? As it turns out, the answer to that is no.
No.
When I the illustration I always made is if I took a pair of 6-inch calipers, I could take a pair of 6-inch calipers, and I could measure the thickness of this piece of aluminum right here, and the thickness of this table, and the thickness of this door right here. With that 6-inch with that set of 6-inch calipers, same measurement equipment, 3 different products, 3 different designs, 3 different materials, right?
Same tolerance?
We'll talk about tolerance in a minute. Okay. But I could have a to the same basic level of precision. I can measure this and that and this, right? Okay, so, and that's what the agency told us when they came in, the Food and Drug Administration. For those of y'all who are not involved with FDA regulated, we have a tendency to refer to the FDA as the agency. When the agency came in, we showed them all these different test method validations. They said, great, which one of these is correct and which 3 of these are wrong? And we said, well, no, they're all right. They said they're different. And they're all measuring contact lens power. So which one of these is correct and which 3 of these are wrong? And we went, and their point was, we need to do our test method validations by the equipment, not specific to the product they're measuring, so long as the product they're measuring is appropriate to be measured by that piece of equipment. So,
Question, so understanding the scenario, you said measuring contact lens power. So some way that the lens is interacting with the light. It's not a contact measurement, right? Or-
no, it's not a
No
contact.
pun. It's a non-contact measurement
Right.
process. Okay.
Yeah. Okay. So Johnson and Cape Medtronic, Director of Quality Assurance, told me, he says, okay, I want you to assess our test method validation methods and make a recommendation. Okay. This presentation I'm about to give is the basis of that investigation and presentation. Okay. What we want to think of, now we have a tendency to use test method validation and measurement systems analysis as synonymous terms. For us, they're synonymous. Basically, we do an MSA in order to complete a test method validation. A measurement systems analysis is an umbrella term, and the concept that I'm going to present here is a structure for the umbrella. Now, I talked about both non-analytical and analytical methods. Can anyone tell me the difference between a non-analytical and an analytical test method? Okay, an analytical test method is a test method for which there is no NIST standard, for which you have to develop a standard for the test. Typically, it's a chemical method. Like, for instance, if I'm going to measure the chemical composition of a specific mix of chemicals, I want to know the different individual chemicals that are in there. I got to know, quite frankly, that this method, typically chromatography, can actually detect and then measure that specific chemical. So for an analytical method, what will happen is the analyst will make up a solution of that chemical and then run it through the chromatograph. Typically a gas chromatograph. It'll burn the chemical, and what'll happen is it'll get a spectrum, right? And it'll say, okay, we have so much of this chemical. They say, great, it does pick up where I want it to pick up. Now what I'll do is I'll test the material I want to test to see if it can detect and quantify the amount of that chemical in that solution. That's an analytical method. We don't do a lot of analytical methods. Who here, does anybody here do analytical methods? Great. Oh, okay. We can talk afterward if you want to talk about analytical methods. This is mostly oriented toward non-analytical methods. Non-analytical methods are methods for which there is a NIST standard. Length, volume, amount of light, amperage, those kinds of things. We, and the pertinent documentation requires that we address at a minimum 4 characteristics for a non-analytical test method. We quantify and address accuracy, precision, robustness, and stability. And we'll talk about each one of those in turn in a minute. As I said, the concept that I'm trying to put together now at RTG, which is the parent group above Medtronic's spine over here, is the concept that as long as I've got a test method that can measure something, and for us, typically when we're talking about measurements of things, we're talking about dimensional measurements. 3-dimensional measurements. as long as I've got a piece of equipment that'll perform that, it doesn't matter what the product is. As long as I've quantified its ability to measure those points, and it does such in such a way that the variability is not too great for the tolerance that we're concerned with. Okay? So, the whole idea is that we make at Medtronic, we have more than 150,000 SKUs of parts we make. Some of those come in families, some of those come individually. If we try to validate by individual product, the number of validations we have to perform is ridiculous. If we can do that, however, by process, by measurement process, how many measurement processes we have? 20, 25, 30, maybe? That makes it a whole lot easier. All we have to do is build an envelope of capabilities of that measurement system and understand the variability that goes along with that measurement. And once we've done that, then as long as that capability, as long as our new product, our new material, our new design is within that envelope, we don't have to do any further validation. Okay? So the idea is that we will perform validation, including the software validation, because obviously a lot of the machines that we use now employ some form of software. And for those of us that are under the aegis of the agency, we have to demonstrate that the software works the way it's supposed to. And then we will transfer that to the using laboratory. Now, in a lot of cases, for us, the developing laboratory and the using laboratory are the same laboratory, so there's no transfer. But picture this. We have, in Medtronic Spine, we have essentially 3 manufacturing facilities that are internal to Medtronic Spine. 4 if you count the one in China. But let's say we go with those 3. Well, one of them has, we have a new product or a new measurement capability, say we get white light, and we get it in all 3 places. Think of how inefficient it would be for all 3 places to write their own procedure, their own test method process, and do a validation in all 3 places. Why can't we have one of them write the process, the method, validate it, and transfer it to the other 2 locations? That way we've got one document, one validation, we save a little bit of money. If we do that over and over and over again, I'm not going to talk to you, Pete. Over and over and over again, we save some money. Yeah, what you got, Pete?
Yeah, so you're going to assume, though, that the environment's the same place to place to place, right?
But and that's part of the validation. We're getting there.
The correlation.
And a test for robustness. Okay? Now, what happens when, okay, we've done the test method validation and we've built that envelope. And we've transferred that method to Deggendorf, to Warsaw, and Puerto Rico. And everybody's happy. And then we get a new product that is outside the envelope. What do? Well, now what we got to do is expand the envelope a little bit to include all that stuff that doesn't fit inside the envelope. And once we do that, now instead of the envelope being this big, now it's this big, then there's probably going to be a long time before we have to expand it again. And eventually we'll get to the point where we don't have to expand it anymore. All we have to do is to continue and check and make sure that that measurement system remains valid.
I do have a question.
And then, let me finish this.
Go ahead.
And then, so consequently, we don't have to do new validations. Yeah, what you got?
So would this, I guess, approach be more savvy for medical devices versus pharmaceutics?
No, it's for
Are you,
we-
so generally you have to determine stability of product to that process.
Well, okay, you're right, you're absolutely correct. But that's part of the analytical test method. That why don't you and I talk about that afterward?
Okay.
Because we, at J&J,
Yeah.
the manufacture contact lens is a chemical process. And
Gotcha.
we have the same problem with organic chemicals that you have with the manufacture of pharmaceuticals. Because I work for a pharmaceutical company too.
Okay.
So we can talk about that, but that's part of the analytical test method process, which addresses additional things. Yes, sir.
So, yeah, before you jump back into it, so, I mean, the basic theory that you're starting out here is that the measurement system is independent of the material being measured, right?
I'm saying so long as it's appropriate to measure that way. Now, obviously, I can't measure something like, for instance,
I can give you an example.
well, no, the example I was going to, I got one. Before I worked for Johnson & Johnson, I worked for a company that made breast implants. Okay, breast implants are made of fairly soft silicon rubber. Okay, obviously I can't measure the thickness of a breast implant shell with a caliper accurately because that's a matter of thumb strength.
Right.
Right.
Well, yeah, and that's exactly where I was
Yeah.
going. So
Yeah.
if you get titanium versus styrofoam.
Absolutely. You've got to make sure that that measurement system is appropriate for the material, for the product. But once you do that, and you've said, okay, I can measure a hole from that big to that big for the right kind of material, the right kind of product.
Yeah, no, I'm totally with you now.
Okay, cool. Okay, so here's the tenets that I proposed for my boss, and we'll go over them one at a time, so don't worry about all this. First one was we need to define what a test method is. A test method is a procedure. It addresses a specific piece or type of equipment, the measurement it performs, the people who do it, and the environment in which it is used. Okay? The environment is very important. Those of us who have been involved with measurement, which is, I have a feeling, the vast majority of us, over time have know that when you take a system out of the right environment, it's not necessarily trustworthy. And we talk about accuracy / bias, precision, robustness, and stability. So, somebody tell me, how do we assess accuracy in a typical measurement system? That's precision. Okay, so how do we assess accuracy?
Against the
The
standard.
standard?
Standard, yeah. We basically, it's calibration, right? We calibrate it to make sure that it agrees with a known standard. Now, is that enough? Sometimes it is. Sometimes it's not. For instance, if you want to make sure that you have essentially linear variability over the range of the instrument, you might do a linearity study. You might do a bias study. Kind of funny story. When I was living in Texas, there was a convenience store that kept getting held up, not too far from where I live. And they could never find the guys who did it, even though they had that scale on the door, you know? Ron White says he's between 6'2" and 6'4", depending on what convenience store he's walking out of. That scale on the door. They knew how tall the people were, right? Until they went over and measured the scale, and they found out that right here where it said 6 feet was actually 5 feet 8 inches off the floor. In addition, what was supposed to be an inch was about 1 1/4 inches. Apparently what had happened was the owner, when the place was new, said, "Put that scale up." And the operator said, "Oh, okay, no problem." And he went over and he went, "Man, I want to make sure this sticks." He never measured to make sure he had the right height, so he had a bias for accuracy. And he wanted to make sure that it stuck, so he stretched it out, so he had a bias, a multiplicative bias, for the interval between the marks. So, sometimes you need to assess bias, in addition to just making sure that at any point, or at several points throughout the range, that you have accuracy. How do we assess precision? You said it a minute ago. How do we assess precision? What is precision?
Repeating the result.
Consistency of results, right? And that's a gauge on our study. Please understand that we get no assessment for accuracy with a GR&R study. You can do it, a system can be repeatable over and over and over and be wrong every time. Robustness. How do we assess robustness?
Multiple users and operators.
Okay, either way. Basically, define a worst case condition, right? Take something you know and measure it in that condition and see if you get the same results. I can guarantee you, when I was working for TI back in the 80s, a lot of our manufacturing, subcontract manufacturing facilities were no more than garage shops. And I remember specifically going to one of those places in August in Dallas. It was 106 degrees outside. It was 90% relative humidity, and they were measuring their product with 6-inch calipers that had been calibrated in a lab at 68 to 72 degrees Fahrenheit and between 30 and 70 degrees relative humidity. Was that 6-inch caliper accurate?
No.
Probably not. Okay, but they had not applied any correction factors. They hadn't assessed the effect of the departure from the known environment. Now, the way we deal with robustness most of the time is we say, we're just not going to use the equipment if we go outside the conditions, the environmental conditions that the manufacturer recommends for its use. Okay? And we've got IQ data, installation qualification data, that says, okay, when we use it in these conditions, we got good results. So that it basically traces back to say, yes, we know as long as we use it in the environmental conditions in which it's intended, that we get good results. That's typically how we establish robustness or address robustness. But if you want to use it out on a shop floor where it's a little bit different, you're going to have to make a determination of what your worst case condition is and assess it under those conditions. Finally, stability. What good is a piece of measurement equipment that is calibrated and has a gauge R&R and then drifts off the next day? No good at all.
That's why I got rid of my acoustic piano.
Okay. I still got mine. Actually, I got another one. At J&J, I was talking about how you do it, the analytical methods. We had a balance that was very precise. It registered 5 decimal place grams. Okay, and we would use it to measure out the chemical that we would mix up to make standards for analytical test methods. And we kept failing analytical test method validations. So finally what we did was we took made up 3 little weights, one that was close to a gram, one that was right at 5 grams, didn't matter what it was because it was close, and one that was close to 9 grams. And we weighed that, each one of those, every day, 3 times a day at the beginning of each shift, and we plotted that on a control chart. And it looked like this. It looked like almost a perfect sine wave. Anybody want to guess what the period of the sine wave was?
24 hours?
Actually, it was 2.5 months. We could never figure out what corresponded with 2.5 months. But the amplitude of the sine wave was almost 3 grams.
Oh my lord.
Okay? So, we told the Metal of Toledo representative, he said, no, it can't be like that. He said, we'll get you a new scale. So, he took that one away, we got a new balance, we did a stability study on that one, it went like that, straight across, all 3. We said, yeah, we can use this one. Okay? So, it's important that you make sure that you continue to get repeatable results day in, day out.
So was it the scale that was the
That's all
problem?
bugging us.
It was a scale.
Yeah.
It was a scale.
You sure you just didn't get the answer you wanted?
No, I'm sure. No, I'm sure because
Okay.
what we did was we used a less precise balance to make up our standards after that, and passed all those test method validations.
Okay.
And then when we got the replacement, it worked fine,
And it was repeatable.
and it was repeatable. Yeah. Okay, this is the pursuant to stability. Make sure the gauge owners monitor their gauges on a periodic basis to make sure they're getting repeatable results. I'm sure most of the labs out there that y'all are associated with do this. Operator turns on the equipment, lets it warm up, and then measures something they've measured before. Okay? Maybe even writes down the results. I would suggest that you put it on an individual moving range chart to demonstrate that you got good, repeatable results over time. Now, this is us, but it's been my experience that quality engineering, not necessarily quality engineering, but quality assurance owns validation. We may not do it, but we own it. Okay, we oversee it, we're responsible for it. Why? Because we are the most knowledgeable individuals in the organization regarding measurement systems. And that includes, that includes computer systems validation, the development of the test methods, the validation, and the transfers. We have to define what a validation is and what a transfer is. Okay? Perform a complete validation for each system. I recommend doing one validation for each, and then the line extension is essentially the growing of the envelope. Okay? Do one test method validation, and then when all of a sudden you're not inside you got something that's not inside the envelope, grow the envelope. That's a line extension. Tenet 5, transfer once. Like I said, we transfer to J&J, we transfer, and every time we got a new product, every time we got a new design, every time we got new material. And the agency asks us which one of these is right, which 4 of these, or 3 of these are wrong, at least at that point. When something comes in, like for instance, you make a change, you find out that, hey, I need to let this warm up 30 minutes instead of 15 in order for it to be stable over time. Great, make a change to the document the way you normally would with any other document, train it, and allow the document control system to handle the changes. This is the recommendation. This comes from Don Wheeler. Anybody here besides me familiar with Don Wheeler? Okay. Wheeler recommends not to use P2T as a capability index. It's flawed. And I'll show you why in a minute. His recommendation is what he calls interclass correlation coefficient.
Just to make sure we're together, P to T percent tolerance?
Precision to tolerance is.
Precision tolerance ratio.
And we'll define that in a minute, Pete. Thank you. Fisher, the stats guy, is the guy who came up with this interclass correlation coefficient. If you use Minitab, it shows up as percent contribution on the second of the three tables on the GR&R chart, and number of distinct categories. And we'll talk about why P to T is flawed in a minute. But basically, the whole idea is that percent contribution is a variance value, not a standard deviation value, and we know that variance is linear. And when you have the variance overall, that's the two components that are the variance of the measurement system and the variance of the part-to-part. Okay? So, you can assess the amount of variance, overall variance, that's due to the measurement system. But it is important that the part-to-part variability represents the tolerance that you're interested in assessing for that piece of equipment. And this comes to tenet 7. The tolerance range, use the entire tolerance range. If you want to assess for that piece of equipment its ability to measure something that is plus or minus 20 microns, make sure that you assess materials that represent approximately plus or minus 20 microns. Because what are the number of distinct categories? It's basically the number of slices in the total variability that you examine, that you can slice, equal size slices, that you can slice that range into and make a discrimination between those parts. The industry standard minimum number of distinct categories is 5. Well, I can guarantee you, I see gauge R&R studies from our suppliers all the time that have one distinct category. Why? They have tolerance on the parts that they're doing the gauge R&Rs for that looks like this, and the parts look like that.
Because they all came off of one run.
They all came off of one run. They're not only do they come off one run, but there's consecutive parts. 1, 2, 3, 4, 5. The other one I love to see is I see all the time, I see studies come in from our suppliers that have 1,387 distinct categories. Okay? What do we have there? We have a tolerance that looks like that and parts that look like this. They use the entire family of parts.
Scratch
They had,
Scrap it all, right?
yeah, scrap it all. But basically, we have parts that are this big, we have parts that are that big. They use the whole family in their gauge R&Rs, the different sizes. Okay? We want it to be representative of the tolerance we want to assess. And when we do that, the number of distinct categories has meaning. This one is not as obvious, but it is a big thing. In the 4.5 years I was at Johnson & Johnson, we used 3 generations of measurement equipment for contact lenses. The first one, it's called a Marco lensometer. If you've ever been to any lens crafters or any of those other places, they say, give me your glasses and I'll measure them. That's what they use. And all it is they put that in the line of light and they adjust it until the image is clear. And that tells them what the magnification is. The problem with that is, for a contact lens, and I'm not going to get into what a diopter is, but for a contact lens, the tolerance for a contact lens typically is plus or minus a quarter of a diopter. But for a young person, you can actually accommodate 1.5 diopters distance, 1 diopter near. So you can accommodate in your eye at least 4 times what the tolerance is. Okay? So we called that piece of equipment, first generation, the dial-a-pass. Okay? The second generation of equipment essentially used a set of moire fringes, equal size lines and spaces. Then they put the lens in there, and that would make the lines and spaces distort, and then what the machine would do is reorient it so the lines and spaces were back the right way. And then it would read backwards what that correction was. That's great. Worked pretty well. The only problem with that is, 1, we could only do 1 lens at a time, and 2, it was limited to the size of the lines and spaces. We needed smaller lines and spaces to get more precision, and we just couldn't get that. So we went to the third level, third generation, which was a laser interferometer, which is essentially that, it's not exactly, but it's essentially that last method with very, 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 very tall, small lines and spaces, because you get constructive and destructive interference. Okay, the problem was, when we did the validation of the third generation machine, we used the calibration tolerance from the first generation machine. And all the improvement and the capability of the third generation machine at first disappeared into the calibration tolerance from the first generation machine. Okay, so if you've got to step up in capability, go back and revisit your calibration tolerance, because it may be too great. Okay, and this was something that we worked on real hard at J&J. When the agency comes in and asks you for some proof of validation, they ask you for a document, their maximum requirement is that you present your proof of validation within 24 hours. Okay? That's bad. If you take 24 hours, they're going to wonder what the heck's going on. At Johnson & Johnson, the requirement was a little bit more stringent. It was 10 minutes. We had to not necessarily have it for the agency, but we had to have it for ourselves to be able to look at it and make sure that we had all the signatures on it and there was no typos and no stupid mistakes before we handed it to the FDA auditor sometime within the first 30 minutes. Okay? We have accomplished this right here at Medtronic by our new